Who's had a look at these questions? That's right. So the first one. Oh, now, what I was going to say is you've got to get your head around this radian. So no longer are we talking about meters, degrees. We're talking about radians. I want you to switch over from degrees to radians. How much is a radian? It's that much, that much, that much. If we've got 3 radians per second, something's doing that, isn't it? It's going through 1, 2, 3 radians in a second, right? So, radians. Now, here's the situation. So we've got a bicycle here like this. It's got has everyone done this as a kid? Well, perhaps not everyone's done it, but you've probably seen it. People put a tennis ball in their spokes like that, in the bicycle wheel. You can imagine a stone getting stuck in your bicycle wheel as well, couldn't you? So if we've got a ball here and a stone here, and it goes through, it rotates through an angle like this, 1 radian. What's a radian, if you missed out on this? Well, whatever this radius is, what did I say the radius was? I've said down here somewhere the radius is 40 centimetres, so this is 0.4 metres. If that's 0.4 metres, what's the distance around there? 0.4, because it's going to go, it doesn't look at, the scale's not great, but 0.4, so it's rotated through 1 radian. Which object has got the greatest rotational displacement? What's rotational displacement? It's how many radians. So this ball, how many radians has it gone through? It's ended up here. How many radians? 1 radian. This stone, how many radians? 1. So which one's got the greatest rotational angular displacement? They've both got the same, haven't they? So this is the beauty behind looking at things from a perspective of radians, because both of these objects have moved the same distance if we're thinking about angular displacement. Now, so the answer to A is, but they're both the same. B, which one's got the greatest linear displacement? Now, hopefully most of you can see that this stone has actually moved further. It's gone that far. This ball has gone that far. Which line is longer? The stone. This one here, look, well, if this is 0.4 metres, this is going to be 0.4 metres, isn't it? 1 radian. That's how far it's gone. This one here, if this is 0.3 metres, and I said it was, it's 0.3 metres, how far has it gone? 0.3 metres. Right, so which object has got the greatest, which has the greatest linear displacement? Well, it's the stone. Next one. If it takes 0.1 seconds to rotate through this 1 radian, what is the angular speed? Now, the formula's not up here, but it's just like linear. It's just like all our linear formulae. You know, like speed is distance divided by time. What's the angular displacement in this case here? It's 1 radian, isn't it? What's the time? 0.1 second. So if I want to work out the angular, just put it up there a little bit, the angular speed, it's the angular displacement, which is 1 radian divided by the time, 0.1 equals 10 radians per second. Right? Fair enough so far? So we've established what the angular displacement is. We've worked out what the angular speed is. If I said angular velocity, how would that change things? Well, which direction is it going? It's going anti-clockwise. So the angular velocity has got a direction, so I would say that the angular velocity is 10 radians per second anti-clockwise. Right, so now, moving on to calculate the linear displacement of the ball that is placed 30 centimetres from the centre of rotation. I've already told you the answer, haven't I? But if I wanted to use the formula, and I put up these 3 formulae here, if I wanted to use the formula, what do I want? Linear displacement. What's D? Linear displacement. You know, we've been used to using D for a long, long time. What's R? R is the radius to the object from where it's pivoting, you know, the pivot point. What's theta? This is the stuff that you've got to now try and remember. Theta is angular displacement. So, what do I calculate the linear displacement of the ball if it is placed 30 centimetres? Do I know what the angular displacement of the ball is? 1 radian. I do know what it is. It's 1 radian. Both those objects have rotated through 1 radian. So I know what that is. So if I want to work out the linear displacement, it's r. What did I say r is? 30 centimetres. Needs to be in metres, 0.3 times theta. What's theta? 1. So the distance is, and this is a pretty simple calculation, but it's 0.3 metres. Right? Just to check, you can use these formulae here. What about the angular velocity? So now, the angular velocity of the stone, if its radius is 40 centimetres. So what's the formula for, I'll calculate that. Oh, I'm a silly Billy. I actually meant, what is the linear? Sorry, if you already looked at that, most of you probably haven't had a chance to look at that, but I mean, what is the linear velocity? So if I wanted to know the linear velocity of the stone, what's my formula? V equals R omega. Do I know what R is of the stone? I've just said I'm in the way, but it's 0.4. Do I know what the angular velocity is? Didn't I calculate it up here somewhere? Angular velocity 10. Look, 10 equals 4 meters per second. So this is in radians per second. This comes out, linear comes out in meters per second. So there's two things going on here. You've got these objects that are rotating through an angle, but at the same time, they're covering a distance and they've got a speed. They've got actually a linear speed. And remember that the linear speed is at a tangent to the circular motion that it's going through, isn't it? So this is the linear speed of the stone at that point there, and it's at a tangent. The only thing I haven't talked about is we can calculate the actual acceleration of things. If we know what the angular acceleration is, then we can work out what the linear acceleration is, and vice versa. And we've already been through those ideas of calculating angular acceleration. What is it? It's change in angular velocity divided by time. Now I think that everyone should be now capable to answer, I think it's pages 49, 50 and 51. Are there any questions about that? Hopefully that's of help. I'll stop that now.